All right. In this module, we will start talking about combinatorics, counting methods, and multiplication principle. So we'll start with a very simple setting. So imagine you have a sample space denoted as S, which has a set of outcomes. So let's say we number the outcomes as integers, outcome 1, outcome 2, up till a certain number of outcomes. I'm going to denote it as the cardinality of the sample space. So cardinality S means the number of elements or outcomes, possible outcomes of an experiment in the sample space S. Now, if you are told, so if all the outcomes in S are equally likely, then this means that the probability of any outcome, say outcome number I, is 1 by the size of the sample space, right? This should be the case because all outcomes are equally likely, and summation of the probabilities of the ith outcome, when I sum up I from 1 till the number of elements in S, should add up to 1, right? So I will have this thing is 1 by the cardinality of S times the number of elements should add up to 1, right? Okay. Okay. Now imagine if you are in a setting where all outcomes in S are equally likely, and then if you define A as some event, and event, remember, is described as a set of outcomes, let's say 3, 5, 11, 13, and so on and so forth. And the number of elements in this event is the size of the set, right? Then the probability of the event A will be the probability of the sum of the probabilities of individual outcomes. In this case, it will be the probability of 3 plus probability of 5, and so on. How many elements are there in the set? Size of A, and each one is of value 1 by the size of the sample space times the cardinality of A, right? So the simple formula is that if you are looking at scenarios where sample space has all equally likely outcomes, then you can readily find the probability of an event A as the ratio of the number of elements in that event divided by the total size of the sample space. So it's a relatively straightforward idea. Okay. So let's move to the next concept, which is called the multiplication principle. Okay, a very simple concept. So I'm going to start with a very simple example first. So suppose you wish to purchase, say, the latest iPhone. And you have the following choices. And you have following choices to pick from. For example, you can pick a large or a small screen. You can pick one of these two options. Then you can pick your storage. Say you can pick 64 gigabyte memory or 128 GB or say 256. And then maybe you can pick the color of your phone. So for example, white or blue or red. Okay. So how many options do you have? So you have 2 options for picking the size of the screen, 3 options for picking the size of storage, and 3 options or 3 choices to pick from color. Okay. So the first, so what we are interested in, we're interested in how many choices do you have to pick your latest iPhone? How many choices do you have? Well, the answer is very simple. You take the number of choices for screen times the number of choices for storage times the number of choices for color, and you get total of 18 choices. Okay, so that's the simple concept of multiplication principle. So you can imagine you can have all possible configurations. So for example, a large iPhone, 64 GB storage, and white color. Large iPhone, 64 GB, blue color. Large iPhone, 64 GB, and red color, and so on and so forth. So if you enumerate all of these out, so for instance, you will have small, 256 GB, and red, and so on. So there'll be 18 such choices or options that you will have to pick from. Okay, and you don't need to write them out. All you do is you multiply the number of choices for screen, number of choices for storage, and number of choices for color, and that will give you the total number of choices to pick from. Okay, so let's write down the more general statement. So the general statement is as follows. Let's write this in a box. So say we perform R experiments, and such that the kth experiment has n sub k possible outcomes. So k goes from 1, 2, all the way till r. So basically you will have n1 choices for the first experiment, n2 choices for the second experiment, all the way till nr choices for the rth experiment. And if you ask what are the total number of possible outcomes, so the total number of possible outcomes will be the product of these number of individual choices that you have, n1 times n2 times n3 all the way till n sub r. Okay, so that's sort of the general idea of multiplication principle. Okay, I'm going to work out another example to explain this concept and also bring in the some concepts from probability that we have learned so far. Okay. All right, so let's work on an example. Suppose you have to pick a password. Password which has to follow the following rules. So you have to pick two lowercase letters, say from little a to little z, followed by one capital letter. So you have options to pick from capital A to capital Z, followed by 4 digits. Any 4 digits of your choice. So you have options 0, 1 till 9 to pick from. Okay. So as an example, x, little y, capital T, 1319 is a valid password. Right? Because it's following these rules, I've sort of given you rules for picking a password. Okay. So let's ask the first question. So first question is, say, how many possible passwords are there? So I'm going to ask, find the total number of passwords, total number of possible passwords. Let's call them N, capital N. So it's straightforward. N is what? So you have to pick two lowercase letters. So N will be, so you have how many letters? A till Z is 26 letters in the alphabet. So I have 26 for the first lowercase option, then 26 for the second lowercase option, right? And then for the third capital letter, I have another 26, and then 4 digits. So 10 times 10 times 10 times 10, right? So these are the two lowercase, one uppercase, and 4 digits. Okay, so this is 26 raised to power 3 times 10 raised to power 4 That's the number of possible passwords. So this is the total number of possible passwords. Okay. Now let's work out another question within the same vein, within this example. Now suppose there is a hacker. So a hacker writes a program to randomly and independently generate say 10 raised to power 8 passwords. So the hacker is going to follow the above rules and start generating random passwords. Okay. Keep in mind that I'm doing it independently, which means that the same password in principle can be generated 2 times. Okay. Now the hacker does this job and sort of prepares these 10 raised to power 8 randomly generated passwords. And if it so happens, so if say one of the above passwords, one of the above 10 raised to power 8 passwords match say your unique password. So let's say you are a student and you generate your own individual password. Your account will be hacked. Okay. So then we can ask this question, let's say, what is the probability that the hacker will be successful to crack your password by just randomly generating 10 raised to power 8 passwords? Okay, so that's the question we're interested in. So we're interested in what is the probability that the hacker is successful? Okay, so we're interested in this question. Okay. So let's break this problem down. Okay. So suppose you have a unique password, so whatever that may be. Now, so in some sense, the hacker is sort of creating 10 raised to power 8 random passwords. So I'm going to create names for events. So I'm going to write G1 as the event that the first password generated by hacker equals your password. Right? G2 is the event that the second password of hacker matches your password, and so on and so forth. So how many events do I have? I have G 10 raised to power 8 such possible events. Keep in mind, your password is fixed. So for example, it could be X, Y, T, 1319, right? So your password is a frozen single number or single sort of string. And then there are these 10 raised to power 8 possible events. Okay. Now let's ask, what's the probability of G sub I, any one of these i's? Well, the probability of G sub I is 1 by n, because the hacker is picking any one of these n possible passwords completely at random, right? So the probability that any one of the password generated by the hacker matches your password is 1 by n. Okay, so hopefully that's clear. Now, what are we interested in? We are interested in the probability of the hacker is successful in cracking your password. So in words, what is this probability? This is the probability that at least one of the 10 raised to power 8 passwords match your password. So not all of them have to match, but even if just one of them matches, then he can log into your account, right? So formally, what is this event? This event is the probability of G1 occurs union G2 union G3 all the way till union G 10 raised to power 8. Okay, so union of event means that If any one of them happens, this is represented by the union of these events. Okay. So we can write this in a slightly more compact way. We can write this as a union over sub I, G sub I, right? I going from 1 till 10 raised to power 8. Okay. So this is the probability that is what we are interested in. So this is the object of interest. Now here is a trick that you should always keep in mind. Okay. So here is a trick to remember. So remember, suppose you're interested in finding probability of union of a bunch of events. Okay. The trick to compute this probability is to look at the complement of this union. So I look at union over I, G sub I. Let's look at the complement of this event. So this is remember from De Morgan's laws, from earlier treatment of this concept. We can write this as the intersection over I of the complement of the GIs. Okay. So this follows from our earlier treatment. So let's break this down. So this is G1 complement intersection G2 complement intersection G3 complement all the way till G sub 10 raised to power 8 complement. Okay. Now let's think about what are these guys. G1 complement is some event which is the opposite of G1. G2 complement is the opposite of G2, and so on and so forth. What else do we know about these events? We know that these events are independent events because all the passwords are generated independently. So these are all independent events. Now we can now apply the axiom of probability, the third axiom of probability. So third axiom of probability tells us that if I look at the probability of the intersection of independent events, we can write it as the product of the probabilities of the events. So this will be this probability of G1 complement times the probability of G2 complement all the way till the product of G 10 raised to power 8 complement. So life is good because now this big complicated intersection can be written as product of very simple terms. What is probability of G1 complement? It is 1 minus the probability of G1. What is probability of G2 complement? 1 minus probability of G2 all the way till the last one. But remember, we computed what is P of G1. P of G1 was 1 by n. P of G2 was 1 by n all the way till 1 minus 1 by n. Now, how many times do I do this multiplication? 10 raised to power 8 times. So what do I get at the end? This becomes 1 minus 1 by n raised to power 10 raised to power 8. Okay. So we have been able to find this probability. Okay. So what we have found so far, we have found the probability of the complement of the union. Okay. What were we interested in? We were interested in the probability of the union. Well, now we are in a good shape. We know probability of hacker successful was the probability of the union of the GIs, I going from 1 to 10 raised to power 8, right? This is 1 minus the probability of the complement of this event, union GI, I going from 1 to 10 raised to power 8. Remember, what principle did we use here? Just as a recap, the principle we use that if, let's say, this is some event A, then this guy is A complement, right? So what we used was probability of A is 1 minus the probability of A complement. That's the principle we used. Very simple idea. Okay. Once we use this fact, then we know we have already computed this guy, which is right up here. So what do we get? We get 1 minus 1 by n raised to power 10 raised to power 8. So this is the probability of hacker being successful. Right? If you plug in the numbers, remember n was 26 raised to power 3 times 10 raised to power 4, then this number is going to come out to be 0.4339, which means there is a 43.39% chance of hacker being successful for this choice of n. Okay, so what I want to emphasize in this module are two things. So first is the multiplication principle, and the second is this trick that whenever you encounter probabilities of union of events, and if you know those events are independent, which is what is happening in this example, then it's always good to look at the complement of the union, and then it's much easier to analyze the complement of that event. Once you have that, then you can just simply go back and subtract that probability of the complement from 1, and then you get back the probability of the union. Okay, so this is sort of the key takeaway from this module. And we'll stop here. Thank you.